So now that we understand what block ciphers are, let's look at a classic example called the data encryption standard. So just a quick reminder, block ciphers basically map n bits of input to n bits of output. And we talked about two canonical examples, triple DES and AES. In this segment, we're going to talk about DES, and we'll talk about triple DES actually in the next segment. And then I also mentioned before that block ciphers are often built by iteration. In particular, we're going to look at block ciphers that are built by a form of iteration where a key K is first expanded into a bunch of round keys, and then a round function is applied to the input message again and again and again. And essentially, after all these round functions are applied, we obtain the resulting ciphertext. Okay, and again, we're going to look at how DES, the data encryption standard, uses this format. I just want to be clear that in fact, to specify a block cipher of this type, one needs to specify the key expansion mechanism, and one needs to specify the round function. In the segment here, I'm going to focus on the round function, and I'm not going to talk much about key expansion, but I just wanted to mention that in fact, key expansion is also a big part of describing how a block cipher works. Okay, so let's talk about the history of DES. Essentially, in the early 1970s, IBM realized that their customers are demanding some form of encryption. And so they formed a crypto group, and the head of that group was Horst Feistel, who in the early 70s designed a cipher called Lucifer. Now it's interesting, in fact Lucifer had a number of variations, but one of the later variations in fact had a key length that was 128 bits and a block length that's also 128 bits. Okay? In 1973, the government realized that it's buying many commercial off-the-shelf computers, and so it wanted its suppliers to actually have a good crypto algorithm that they could use in products sold to the government. So in 1973, the National Bureau of Standards, as it was called at the time, put out a request for proposals for a block cipher that's going to become a federal standard. And in fact, IBM submitted a variant of Lucifer. That variant actually went through some modification during the standardization process. And then finally, in 1976, the National Bureau of Standards adopted DES as a federal standard. And in fact, for DES, it's interesting that the key length was far reduced from Lucifer. It's only 56 bits, and the block length was also reduced to 64 bits. And in fact, these decisions, especially the decision to reduce the key length, is kind of the Achilles heel of DES and was a source of many complaints over its life. In particular, already back in 1997, DES was broken by exhaustive search, meaning that a machine was able to search through all 2 to the 56 possible keys to recover a particular challenge key. And in fact, we're going to talk about exhaustive search quite a bit. It's quite an interesting question, and there are various ways to defend against exhaustive search. And basically, this 1997 experiment kind of spelled the doom of DES. It meant that DES itself is no longer secure, and as a result, the National Institute of Standards, as it became known, issued a request for proposals for a next generation block cipher standard, and in 2000 it standardized on a cipher called Rheindahl, which became the Advanced Encryption Standard, AES, and we'll talk about AES later on. But in this segment I want to describe how DES works. Now DES as a cipher, it's an amazingly successful cipher. It's been used in banking industry. In fact, there's a classic network called the Electronic Clearinghouse, which banks use to clear checks with one another, and DES is used for integrity in those transactions. It's also used in commerce. In fact, it was very popular up until recently as the main encryption mechanism for the web. Of course, now that's been replaced with AES and other ciphers. Overall, it's a very successful cipher in terms of deployment. DES also has a very rich history of attacks, which we'll talk about in the next segment. Okay, so now let's talk about the construction of DES. So the core idea behind DES is what's called a Feistel network, due to Horst Feistel. And basically, it's a very clever idea for building a block cipher out of arbitrary functions f1 to fd. Okay, so imagine we have these functions f1 to fd that happens to map n bits to n bits. Now these are arbitrary functions. They don't have to be invertible or anything. What we want to do is build an invertible function out of those d functions. And the way we'll do it is by building a new function, we'll call it capital F, that maps 2 n bits to 2 n bits. And the construction is described right here. So here we have our input. You notice there are 2 blocks of n bits. In other words, the input is actually 2 n bits. The R and L stand for right and left. Typically, people describe a Feistel network from top to bottom, in which case these n bits really would be right and left. But here it's more convenient for me to describe it horizontally. So if we follow the R input, you realize it basically gets copied into the L output without any change at all. Okay? However, the L input is changed somewhat. Basically, what happens is the R input is fed into the function F1, and the resultant is XORed with L0, and that becomes the new R1 input. Okay, so this is called one round of a Feistel network, and it's done using the function F1. Now we do this again with another round of the Feistel network with the function F2, and we do it again and again and again till we get to the last round, and we do it again with the function Fd, and finally the output is Rd Ld. Okay, so if you like, we can write this in symbols, that basically Li is simply equal to Ri minus 1, and Ri, let's see, that's the more complicated one, Ri is equal, well, let's just follow the lines here, Ri is just equal to Fi applied to Ri minus 1 XOR Li. Okay, so and this is basically I goes from 1 to D. So this is the equation that defines a Feistel network mapping a 2 n-bit input to 2 n-bit output. So here we have again, I just copied the picture of the Feistel network, and the amazing claim is that in fact it doesn't matter which functions you give me. For any functions F1 to Fd that you give me, the resulting Feistel network function is in fact invertible. And the way we're going to prove that is basically we're going to construct an inverse, because not only is it invertible, it's efficiently invertible. So let's see. So let's look at one round of a Feistel network. So here, this is the input, Ri, Li, and this is the output, Ri plus 1, Li plus 1. And now what I'm going to ask you is to invert this. So let's see. So suppose now the input that we're given is Ri plus 1, Li plus 1. And we want to compute Ri, Li. So we want to compute the round in the reverse direction. So let's see if we can do it. Well, let's look at Ri. So Ri is very easy. Basically, Ri is just equal to Li plus 1. So Li plus 1 just becomes Ri. But now let me ask you to write the expression for Li in terms of Ri plus 1 and Li plus 1. So I hope everybody sees that basically Li plus 1 is fed into the function Fi plus 1. The result is XORed with Ri plus 1, and that gives the Li input. So this is the inverse of one round of a Feistel network. And if we draw this as a diagram, let's just write the picture for the inverse. So here you notice the input is Ri plus 1, Li plus 1, and the output is Ri, Li, right? So we're inverting the round. So you notice that the inverse of a Feistel round looks pretty much the same as the Feistel round in the forward direction. It's literally, just for a technical reason, it's kind of the mirror image of one another, but it's basically the same construct. And when we put these inverted rounds back together, we essentially get the inverse of the entire Feistel network. So you notice we start off with round number D, with the inverse of round number D, then we do the inverse of round number D minus 1, and so on and so forth, until we get to the inverse of the first round, and we get our final output, which is R0, L0. Right? This is the input, and we manage to invert basically RD, LD, and get R0, L0. And the interesting thing is that basically the inversion circuit looks pretty much the same as the encryption circuit, and the only difference is that the functions are applied in reverse order. Right? We started with Fd and ended with F1, whereas when we were encrypting, we started with F1 and ended with Fd. So for hardware designers, this is very attractive because basically if you want to save hardware, you realize that your encryption hardware is identical to your decryption hardware. So you only have to implement one algorithm and you get both algorithms the same way. The only difference is that the functions are applied in reverse order. Okay, so this Feistel mechanism is a general method for building invertible functions from arbitrary functions F1 to Fd. And in fact, it's used in many different block ciphers, although interestingly, it's not actually used in AES. So there are many other block ciphers that use a Feistel network. Of course, they differ from DES in the functions F1 to Fd, but AES actually uses a completely different type of structure that's actually not a Feistel network. We'll see how AES works in a couple of segments. So now that we know what Feistel networks are, let me mention an important theorem about the theory of Feistel networks that shows why they're a good idea. This theorem is due to Luby and Rockoff back in 1985, and it says the following. Suppose I have a function that is a secure pseudo-random function. Okay, so it's indistinguishable from random and happens to act on n bits. So it maps n bits to n bits and uses a key k. Then it turns out that if you use this function in 3 rounds of a Feistel network, what you end up with is a secure pseudo-random permutation. In other words, what you end up with is an invertible function that's indistinguishable from a truly random invertible function. And I hope you remember that the definition of a secure block cipher is that it needs to be a secure pseudo-random permutation. So what this theorem says is if you start with a secure pseudo-random function, you end up with a secure block cipher. Basically, that's what this says. Now let me explain in a little bit more detail what's actually going on here. So essentially, the PRF is used in every round of the Feistel network. So in other words, here what's actually computed is the PRF using one secret key, K0. Here what's computed is the PRF using a different secret key, of course applied to R1. And here we have yet another secret key, K1 applied, K2 applied to R2. And you notice this is why basically this Feistel construction uses keys in K cubed. In other words, it uses 3 independent keys. So it's very important that the keys are actually independent. So really we need 3 independent keys. And then we end up with a secure pseudo-random permutation. Okay, so that's the theory behind Feistel networks. And now that we understand that, we can actually look at the specifics of DES. So DES is basically a 16-round Feistel network. Okay, so there are functions F1 to F16 that map 32 bits to 32 bits, and as a result, the DES itself acts on 64-bit blocks, 2 times 32. Now, the 16 round functions in DES are actually all derived from a single function f, just used with different keys. So in fact, these are the different round keys. So ki is a round key, and it's basically derived from the key k, derived from the 56-bit DES key k. Okay, and I'll describe what this function f is in just a minute. But basically, you see that by using 16 different round keys, we get 16 different round functions, and that gives us the Feistel network. So just at a high level, how the DES works, basically you have a 64-bit input. The first thing it does is this initial permutation that just permutes the 64 bits around, namely it maps bit number 1 to bit number 6, bit number 2 to bit number 17, and so on. This is not for security reasons, this is just specified in the standard. Then we go into the 16-round Feistel network that actually you now know how it works. Basically uses the function f1 to f16 as specified before. And then basically we have another permutation. This is called the final permutation. That's just the inverse of the initial permutation. Again, it just permutes bits around. This is not necessary for security reasons. And then we finally get the final outputs. Okay, now as we said, there's a key expansion step, which I'm not going to describe. But basically this 56-bit DES key is expanded into these round keys, where each round key is 48 bits. Okay, so we have 16 48-bit round keys, and they're basically used in the 16 rounds of DES. And then when you want to invert the cipher, all you do is you use these round keys, these 16 round keys, in reverse order. Okay, so now that we understand the DES structure, the only thing that's left to do is specify the function capital F. So let me explain how this function works. So basically it takes as inputs its 32-bit value, let's call it X, but in reality you remember this is R0, R1, R2, R3, and so on and so forth. These are 32-bit values. And then it takes also a 48-bit round key. So here we have our key Ki, which happens to be 48 bits. The first thing it does is it goes through an expansion box. And this expansion box basically takes 32 bits and maps them into 48 bits. Now all the expansion box does is just replicate some bits and move other bits around. So for example, bit number 1 of X is replicated into positions 2 and 48 in the output. Bit number 2 of X is positioned in as bit number 3 of the output. And so on and so forth. Just by replicating some of the bits of X, we expand the input into 48 bits. The next thing we do is we compute an XOR with a round key. Sometimes people say that cryptographers only compute XORs. This is an example of that, where, well, we just do XORs in this function. And then comes the magic of DES, where actually these 48 bits are broken into 8 groups of 6 bits. 6, 7, 8. And so let me draw. And then what happens is, so each one of these wires is 6 bits. And then they go into what are called S boxes. And I'll explain the X boxes in just a minute. The X boxes are kind of the smarts of DES. S8. And then the S boxes basically map 6 bits to 4 bits. So the outputs of the S boxes are these 4 bits. They're collected. This gives us 32 bits, right? 8 groups of 4 bits gives us 32 bits. And then finally, this is fed into yet another permutation, which just maps the bits around. So for example, bit number 1 will go to bit number 9, bit number 2 will go to bit number 15, and so on. So it just permutes the 32 bits around, and that's the final 32 bits output of this f function. Okay? So by using different round keys, essentially we get different round functions, and that's how we form the 16 round functions of DES. Now, the only thing that's left to specify are these S boxes. So the S boxes literally are just functions from 6 bits to 4 bits, and they're just implemented as a lookup table, right? So describing a function from 6 bits to 4 bits basically amounts to writing the output of the function on all 2 to the 6 possible inputs. 2 to the 6 is 64, so we just have a table that literally contains 64 values, where each value is 4 bits. So here's an example. This happens to be the 5th S box. And you see that this is a table that contains 64 values, right? It's 4 by 16. So 64 values. And for example, if you want to look at the output that corresponds to 0, 1, 1, 0, 1, 1, okay, then you look at these 2 bits. This is 0, 1. And you look at these 4 bits. This is 1, 1, 0, 1. And you see that the output is 1, 0, 0, 1. The 4 bits output 1, 0, 0, 1. Okay, so the S boxes are just implemented as these tables. Now the question is, how are these S boxes chosen? How are these tables actually chosen by the designers of DES? To give you some intuitions for that, let's start with a very bad choice for S boxes. So imagine the S boxes were linear. What do I mean by that? I mean that imagine that these 6-bit inputs literally were just XORed with one another in different ways to produce the 4-bit outputs. Okay, another way of writing that is that we can write the S box as a matrix vector product. So here you have the matrix AI and the vector, the 6-bit vector X. And you can see that if we write this matrix vector product, basically we take the inner product of this vector with the input vector. Remember, these are all bits. So the 6-bit vector, inner product, another 6-bit vector, and we do that modulo 2, you realize basically what we're computing is x2, XOR x3. Right? Because only position 2 and position 3 have 1s in it. And similarly, the next inner product will produce x1, x4, x4, XOR x5, and so on and so forth. Okay, so you can literally see that if the S boxes are implemented this way, then all they do is just apply the matrix A to the input vector x, which is why we say that in this case the S boxes are completely linear. Now I claim that in fact if the S boxes were linear, then DES would be totally insecure. And the reason is, if the S boxes are linear, then all that DES does is just compute XOR of various things and permute and shuffle bits around. So it's just XORs and bit permutations, which means that as a result, all of DES is just a linear function. In other words, there will be a matrix B of these dimensions. Basically, it's a matrix B that has width 832. Basically, what I would do is I would write the 64-bit message plus the 16 round keys as one long vector, right? So the message is 64 bits, and there are 16 round keys, each one is 48, and that, if you do the math, it's basically 832. Okay, so I write these guys, the keys and the message, as one long vector, and then there would be this matrix that essentially, when you compute these matrix vector products, essentially you get the different bits of the ciphertext. So there's 64 of these rows, and as a result, you get 64 bits of ciphertext. Okay, so this is what it means for DES to be linear. So if you think a little bit about this, you realize the S boxes are the only nonlinear part of DES. So if the S boxes were linear, then the entire circuit is linear, and therefore it can be expressed as this matrix. Now, if that's the case, then DES would be terrible as a secure pseudo-random permutation. And let me give you a very simple example. Basically, if you take the XOR of 3 outputs of DES, well, let's think what that means. Basically, we would be looking at B times the matrix B that defines DES times one vector, XOR B times another vector, XOR B times a third vector. We can take the B out of the parentheses, so we'd be basically doing B times this vector over here, but of course K XOR K XOR K XOR K, this is just K. And so if you think about what that means, basically we just got back DES of K at the point M1 XOR M2 XOR M3. But this means that now DES has this horrible relation that can be tested, right? So basically if you XOR the output of three values M1, M2, and 3, you'll get the value of DES at the point M1 XOR M2 XOR M3. Now this is not a relation that's going to hold for a random function. A random function is not going to satisfy this equality, and so you get a very easy test to tell you that DES is not a random function. And in fact, it's not even, maybe you can take that as a small exercise, it's not even difficult to see that given enough input-output pairs, you can literally recover the entire secret key. Yeah, you just need 832 input-output pairs, and you'll be able to recover the entire secret key. And so if the X boxes were linear, DES would be completely insecure. It turns out, actually, even if the X boxes were close to being linear, in other words, the S boxes were linear most of the time, so maybe for 60 out of the 64 inputs, the S boxes were linear, it turns out that would also be enough to break DES, and we're going to see why later on. In particular, if you choose the S boxes at random, it turns out they'll tend to be somewhat close to linear functions. As a result, you'll be able to totally break DES. You'll just be able to recover the key in basically very little time. And so the designers of DES actually specified a number of rules they use for choosing the S boxes. And it's not surprising, the first rule is that these functions are far away from being linear. Okay, so in other words, there is no function that agrees with a large fraction of the outputs of the S box. And then there are all these other rules. For example, they're exactly 4-to-1 maps, right? So every output has exactly 4 preimages, and so on and so forth. So we understand now why they chose the S boxes the way they did. And in fact, it's all done to defeat certain attacks on DES. Okay, so that's the end of the description of DES. And then in the next two segments, we're going to look at the security of DES.